I was at the cryptographers panel this morning, and Diffie was the moderator, and he said that FHE, so fully homomorphic encryption, is one of the jewels we have in crypto. And I kind of agree, so that's a beautiful technology. So I present you TFHE. So TFHE is one of the fully homomorphic encryption schemes that we use in practice. So this is a quite efficient one. And I will focus on a public key variant of it. So we all care about privacy, but we shouldn't. So privacy should be there by design. And the beauty of FHE is that it allows you to do so. So you'll see a practical example of FHE and how it allows you to get privacy for free. So if you don't know what is FHE, so FHE is encryption. So it means that you can encrypt, and then you can decrypt. So you see that I'm using the same key to encrypt and to decrypt. So this is symmetric key encryption. But of course, so you can also do the same using a public key. So usually when you encrypt, you get a ciphertext, and the ciphertext is just something that looks random. So you can do nothing with a ciphertext. You can just decrypt, that's it. Fully homomorphic encryption allows you to do more. So we have also an evaluation key, so that's a public key. And that key allows anyone to compute any function on the ciphertext. So it means that if you're given the encryption of x, anyone can compute the encryption of f of x. That's beautiful, no? And so this is for just one ciphertext, but you can do the same if you're given multiple ciphertexts. So if you're given the encryption of x1 and x2, so then you can also get the encryption of any function of x1 and x2. So as I told you, so this is symmetric key cryptography, but in the case of fully homomorphic encryption, so there is a trick that allows you to turn any symmetric key encryption into a public key encryption scheme. Okay, so TFHE. So there will be some math in the presentation, so I'm sorry for that. So if you want to encrypt a message M, so first you choose some random mask. So a mask is just a vector in ZQ. Just to give you an ID, so the size of N is 1,000. So you see that the mask is pretty large. The message is M. So the message, you can see it here. So this is the message. So the message is put in the higher bit of that string here. And then for security reasons, so we have to add some noise. So here's some noise that is added onto this get message M, and then you get mu. And to get the second part of the ciphertext, so you compute the inner product of A, so the mask, and S. So S is the secret key. You add mu, and then you get the body B. And the ciphertext is that pair A and B. So you see that this is pretty fast to do. So what you have to do, so is just computing basically that inner product. So now to decrypt, so just do the same but in the other direction. So you start with the ciphertext A and B. Then you compute the inner product of A and S, so the secret key. You subtract that value from B, you get mu. Then you round mu, and you get the input message M. So that works if the error here, E is not too large. So too large means smaller than delta over 2. Okay? And so you see, so the security of the scheme is based on lattices. And the reason all FHE schemes we know are using lattices is because decryption is super easy. And an operation that you have to do using FHE is called bootstrapping. And bootstrapping means homomorphically evaluating the decryption. And for that, so the decryption algorithm should be simple. So this is why all the instances of FHE we know are based on lattices. So, so that was private key encryption, the previous one. So now if you want to have public encryption, so that anyone can encrypt, so there is no secret to encrypt. So what you can always do, so just define the public key as a bunch of encryption of 0. So this is the public key, so you want up to UZ or encryption of 0. And then to publicly encrypt a message M, so you first choose a random binary string, R1 up to RZ. Then you compute the linear combination of those public key elements here. Then you compute what is called a trivial encryption of message M. So trivial encryption in this case means that you don't have to know the secret key to encrypt. And this is easy in the case of FHE. So if you look at the scheme, in this case, so you see that if you take the mask A equal to 0, so the inner product of 0 and S, this is equal to 0. And so you see that you can take, and you can show 0 for the noise. So it means that you can take for the mask 0, and for the body, just delta times M. So you see that this is a valid encryption of message M, because when you decrypt that pair, you get back the input message M. So this is called the trivial encryption of a message. So last step, so just add those two, so that S and that trivial encryption, and then you get your ciphertext. So again, this is very fast. Drawback is that this is very large. So if you look at the size of Z here, so you can see that the larger the value of Z is, the better the security is, but also it also increases the running time. And so what is the minimal value we have for Z is this. So this is given by the leftover lemma. So this is the LWE dimension, small n, so typically this is 1000. Times Q, so the binary length of Q, so this is typically 64, and kappa is the security parameter, so security level, so 128 in this case. And if we take typical parameters, so the size of the public key is pretty large, so more than 500 kilobytes. So question is, can we do better? And this is what I present you. So I'll show you how to modify the scheme so that we also have ciphertext of LWE type. And this is quite important because then it means that we don't have to change anything to TFHE, so it will work just as before. So public key will be much shorter, as you'll see. And as a bonus, so we also have less noisy ciphertext. So it is also something good to have. And the scheme is probably secure. So the secret ingredient we'll be using is special convolution. So if you're given two vectors, U and V, so you can define a convolution, so that will give you another vector W. And this is the way the component of W are defined. And this comes with some nice properties. So the first one is that you have something that is almost commutative. So when I put an harpoon here on top of a vector, it means that you just look at the vector, but in the opposite direction. So it means that you just read the vector backwards. What is also something nice is that the last component of that vector is just the inner product of the two input vector, U and V. And the last property that is also very useful is that you have something close to associativity, you see? So you can swap U and V in this case. And so now if I want to publicly encrypt, so key generation works as follows. So the input public key, as before, is just a binary string. So again, of size typically 1000. We choose some random noise vector E. Then we compute the mask A. So A is a random vector in ZQ of size n. And then we compute the second part. So this is a vector. So we compute the convolution of A and S plus that random noise E. And the public key is those two is the pair of those two vectors, A and B, and the secret key is S. So now to encrypt the message M. So first, we choose a random binary string R, some random noise E1, so this is a vector, another random error E2. Then you compute a mask. So the mask is the convolution of A and R plus some noise, so that noise E1. And then the body, so we compute the inner product of B and R. We add the encoding of the message M, so which is delta M plus that error parameter E2. And A and B is a ciphertext. And so what is very nice is that if we compute the encryption of M like this, so this is an LWE type ciphertext. So it means that to decrypt it is just as a regular LWE ciphertext. So just compute the inner product as before of S and A, subtract it from B, then you get mu, then you run mu, and you get back the input message M. You see? Okay. So I won't present the proof, but it's not too difficult to show. So the scheme is semantically secure, and under the ring LW is assumption. So you may wonder why we see a polynomial here. And the reason is that there is a close relation between the convolution and the multiplication in this ring. So actually, there is an isomorphism between that vector space and that polynomial ring. So given a vector U, so you can associate the corresponding polynomial here. And the convolution of a polynomial n, so another vector, of a vector and another vector, but in the reverse direction, give you something that is homomorphic to the product of two polynomial U and V. In the case of TFHE, so as I told you, so one of the operations is the bootstrapping. And for the bootstrapping, so we need to assume the ring LW assumption. So in this case, so because we'll be at some point bootstrap ciphertext, so this is not an additional assumption. So this is an assumption that we are already using. So this is not weaker than the usual TFHE scheme. Now regarding the performance, so remember that with the direct approach, so the size of the public key was more than 500 kilobytes. In this case, so we have something that is about 8 kilobytes. So you see that there is a big difference between the original scheme and the new one. Also regarding the noise, so you see that we gain more than 2 bits, I mean, which is always something good to have. So in this case, this is for 64 bits ciphertext modulus. And sigma in this case, so this is the standard deviation. So we are taking always Gaussian noises. Okay. So this was for special convolution, but actually we can generalize that result. So we can take actually any polynomial ring. So in this case, so I mean the convolution was based on that ring. So n is the power of 2, so this is a cyclotomic polynomial. But actually, you can take any irreducible monic polynomial, so you'll get another convolution, and from that, you can define a new public key encryption scheme. And a good example is cyclotomic polynomial. In particular, if you take n to the power of 3, so then you have that polynomial, and then again, so you get a new way to publicly encrypt messages. There are some advantages of considering those extended polynomial, and this is if you want to rely on the entity for speeding up the convolution. So typically in TFHE, so Q is a power of 2, so 2 to the 64, and n is also a power of 2. But in that case, you cannot use the entity because I mean the two values should have to be coprime. So it is better to choose for n a power of 3, in which case you can use the entity to speed up the convolution. Also, I was assuming that S was a binary string, but you can take a more general string. So again, because there is that bootstrapping operation, so to make it faster, typically we choose small value for S, so like binary, but you can also have a ternary distribution. If you use automorphism, then you can take more general distribution for the private key S. But for the randomizer, so R, so that one has to be taken from a small subset, so as a binary string, so as I showed you, but or as a vector value between -1, 0, and 1. And the reason to choose small value for the randomizer is to control the noise. So if you want to avoid that, so then you have to rely on tricks like gadget decomposition. But then, so this will also impact the performance. So it's better to choose the randomizer in a small subset of ZQ. Okay. So what I showed you was to encrypt one message, but in many applications, we have to encrypt multiple messages. And so unlike private key encryption, so for FHE, it's not easy to compress the ciphertext. So in the case of, so maybe I can show you because that's quite easy. So if you take the symmetric key TFHE, so this one. So actually, so I told you that the ciphertext is that vector, A and B. So if you want to compress that ciphertext, so what you can choose, instead of a vector A for the mask, you just choose a random string, and then you compute the mask using a PRF that you apply to that string. So for example, hash function. Okay? So you can use just a seed, sigma, then you apply some hash function to compute the mask A, and the ciphertext is just that random seed, sigma, and B, the body. And then to reconstruct the ciphertext, so if you are given the seed, you can recover the complete mask. That does not work with public key encryption, so that's a pity. So it means that there is no easy way to compress the ciphertext. But what you can do, you can pack multiple ciphertexts together. So in the usual approach, so if you want to encrypt Z plain text, so this is the total size of your ciphertext, so Z times N plus 1. So again, N is the dimension of the LWE, and Q is the ciphertext modulus. So you can improve on this, and so this is what you get at the end. So just to give you an idea, so if you take, for example, Z equal to N, so the naive approach will require N squared times the size of Q bits. In this case, so you see that you replace n squared by 2n, which is a big improvement. So remember that n typically is 1000. So the way it works, so if you want to encrypt, in this case, Z messages, so you take, as before, a random string R, two noise, so E1, E2, then you compute the mask, just as before, and the computation of the body is slightly different. So you first compute B1, just as before, and for the other one, so for all the remaining messages, you compute it in this way, and instead of taking the inner product, we just take the corresponding components of the convolution. And to send your ciphertext, so you just send that mask, A, and all those bodies. So only the first one, so A and B1 is a LWE ciphertext. For the other ones, so for the other body, so you have to apply some public map on the mask to get the corresponding LWE ciphertext. This is a very fast operation, so this is almost for free. So this is a very good way when you have to encrypt multiple messages. And to conclude, how much time do I have?
You have 23 minutes.
Left?
For the session, yeah.
Ah, for the whole session?
The whole time.
But not just for me?
No, not just for you.
Okay, cool.
For both of you.
Perfect. So I just presented a public key variant of TFHE. So the main advantage is the size of the public key, which is much smaller. Ciphertexts are slightly less noisy, and so it's probably secure. Also showed some generalization extension, how to encrypt multiple messages. And so the reason I look at that problem is for something we are doing at Zama, so it's called FHEVM. So this is a way to evaluate smart contract using homomorphic encryption. So one of the big disadvantage of, but also something that is needed for blockchain application is that everything is public. So in this case, so what we do, so we do everything but over encrypted data. So you are given your smart contract, everything is encrypted, and you just evaluate your smart contract over encrypted data. So there is no leakage. And that's it. Thank you. Other questions or comments?
Hi. Great talk, by the way. Can you tell us a little bit about the efficiency of the bootstrapping on TFHE?
Yeah, so on my laptop, which is regular Mac, so it's 10 milliseconds.
Sorry?
10 milliseconds for bootstrapping.
Thank you.
Yeah.
What do you think some of the impediments are to adoption of these protocols in the market? Like you made it pretty straightforward. Like, what do you think we need to kind of clear the path and make this more commonplace?
Okay, so so for us, the most direct application is blockchain, because if you look at smart contract, I mean, it's too difficult. I mean, the type of operation you are doing are pretty easy. So for that, FHE is already ready for production. And the other application, but this one is more longer term, is machine learning. So if you look at inference, so for, I mean, basic model like, I don't know, linear regression, I mean, something very simple. I mean, this is super efficient. For neural networks, it's also quite efficient. I mean, depends, of course, on the depth of the network. Regarding LLM, so we were not yet there, but I think the main, the game changer is acceleration and As you know, so DARPA is injecting a lot of money on hardware acceleration for FHE. So we hope to get two other, maybe three, order of magnitude of, to speeding up the computation. And the faster you go, so the more per application so you can address. So to give you an idea, so the difference between computation over key data versus computation over encrypted data, of course that depends on the application, but just to give you an idea, so it's something like 10,000. So 10,000, yeah, depends. So this is what state of the art today. So for some application, that's good enough. So, if you have something that is super fast, so if you are, 10,000 slower, that's okay.
So can you tell us more about how do we know that we need to do a bootstrap? Like, how do we know that we consumed enough, We now need
okay.
The noise. Can you tell us more about the noise and how do you know that you need to do the bootstrapping?
Okay. So, so of course I like the ciphertext. So yeah, that's a good one in this case. So usually when you do computation over encrypted data, so the noise tends to grow. So for example, addition, increase the noise but not too much. Multiplication, quite a lot. And so, this is the noise. So as long as you don't touch the message, you're good. And so when you're doing computation, so you know in advance what will be the effect on the noise. So you know when you need to bootstrap. So if you have to do this by hand, this is pretty difficult. So we also have tools to do that, to automate that process. So you are given, input, the computation you have to do, and then it will provide the right secret. So I'm telling when to bootstrap the ciphertext. Good? Yeah? Okay, thank you.
Hi, I'm Tabitha. I'm a PhD student at the University of London. I'm really happy to be here talking to you about this work, which I completed while I was at Intel Labs. I know I just said I did it while I was at Intel Labs, but they don't endorse it, so there should be a disclaimer. I'm not speaking on behalf of Intel Labs. I'm speaking in a personal capacity. Cool. Yeah, so Marc did a great job talking about homomorphic encryption. I'm going to retread the ground a little bit because I didn't know which one of us was speaking first. So I hope you'll give me some patience. Thank you. Okay. So in my title, I've got quite a lot of words. So I'm going to go through them now. I'm going to start with homomorphic encryption. And I'm going to introduce, what I consider the maybe canonical use case for homomorphic encryption. There's lots of others, but this is, the use case it was designed thinking of. So we have a user, and we have a server. I'm going to keep it really simple. The user sends a request to the server, and they get back a response. Wow, easy. But if we're thinking about privacy for the user in this case, what's the problem? What's the issue? Well, in some cases, even the server seeing the request is a privacy breach, right? For example, suppose the user has some medical data and they want to get a prediction on that medical data, do I have risk factors? Maybe it's genomic data. Maybe they want their credit score. They want to see their credit score, but they don't really want to be sharing the information that goes into a credit score. Maybe they want to set a new password and they want the server's opinion on, is this a strong password? But they don't really want to be, disclosing potential passwords. The simplest way we can inject privacy is we just encrypt the request, right? Now the server can't see it. But can the server still use that data? Well, if we use homomorphic encryption, the magic is, yeah, they can. The server can compute on the request while it's in this encrypted state and send back an encrypted response. And it's encrypted with a key that only the client knows. This is great, right? It's not quite this easy, but it's close enough for today. Okay. The second technology I'm talking about is differential privacy. The setting for differential privacy is a little different. We have a database here, we have a function here, and we have a result. Great. And differential privacy is concerned with the question of if all an onlooker sees is this result, can they tell if an individual was in the database? Is it really easy for them to tell? This is pretty powerful, right? If I'm sharing the results of, my quarter, but people can reconstruct my database, that's a pretty major privacy breach. Differential privacy is pretty widely used. I would say it's quite a bit more established than homomorphic encryption at the moment. I've got some examples. The US Census Bureau releases kind of summary statistics, and they use differential privacy to make sure that no one's records can be reconstructed. The IRS does something similar. Apple does this, actually. Apple knows what the most popular emojis are, but they don't know what any one user's emoji usage is. So I guess we can think of differential privacy as you know something about the population, but you don't know anything about the individual. Yeah. Cool. Okay. So yeah, let's keep going. So this is a kind of candidate data pipeline. It might not look like your data pipeline. I'm sorry about that. We have this acquisition stage where we gather some data, might be from public sources, maybe private sources. We clean it up a little. We do some initial exploration to work out what kind of modeling we want to do. Then we actually do the modeling. And finally, and this is missing from some graphics like this, we do present the results, right? We don't just do the modeling for our own enjoyment. We actually share those results with someone. So these are the 5 stages. So kind of, given the 2 technologies I've introduced, if I'm worried about privacy leakage at this stage, at my modeling stage, which of the 2 technologies I've introduced would be a good candidate to kind of guide against privacy breaches at this stage? Okay, I won't leave you in suspense. It's homomorphic encryption, right? It's a nice shield against these kind of adversaries. I can do this modeling while it's still encrypted. Okay? And then I would argue that if I'm worried about privacy leakage for my data at this stage, the kind of standard technique would be differential privacy, right? Okay. Cool, but yeah, let's keep this in mind. Great. Okay, so in this work, our contributions are about, whether we can get differential privacy for free by using homomorphic encryption. That's kind of the research question. And to talk about that a little more, Marc's done a great job talking about noise, but I've got to talk about it again. So popular homomorphic encryption schemes rely on the learning with errors or ring learning with errors problem. For our purposes, we don't need to know too much about this, but we do need to, what I'm going to highlight is that it means we add noise during encryption, which grows during computation or changes during computation. And then on the flip side, a popular technique for achieving differential privacy is adding enough noise that kind of any single individual is obscured. We kind of randomize a little bit. And the kind of goal of this work is to make an identification between these 2 noises. Can we say that the noise in homomorphic encryption means that we have differential privacy for free? So going back to our pipeline, what I'm kind of asking is, can we say that because we used homomorphic encryption here, we have differential privacy here? It'd be great if we could. And the answer is yes. We prove a couple of theorems about differential privacy in this setting. But it's a little challenging. I wouldn't Yeah, maybe some more work needed on this. But I'll run you through kind of what the challenges are, and it will maybe give you a bit more insight into noise and homomorphic encryption. Okay. So the first complication is that homomorphic encryption noise is typically very small. I mean, like in homomorphic encryption, we don't want it to be there. We have to have it for security. So we've got all these techniques to keep it really, really small, like bootstrapping is one of them. And in a lot of schemes, the noise is actually removed entirely. So it's not even there to give us that differential privacy. So we're going to have to make choices that mean this isn't a concern. So we need to choose a scheme where noise grows. Well, we can do that. That's fine. It's fine. Okay, we're over the first roadblock. The second is that homomorphic encryption noise is pretty difficult to model, as in to say what the distribution of it is. And for differential privacy, we do need to make claims about that. But we can make some heuristics, and we can back them up, and can be happy. But this third one is a bit more of a killer. So it's that the way homomorphic encryption noise grows is dependent on the database that was used. It's a bit of a long sentence, but what I'm saying is that the noise we get out changes based on the database we put in. So this is kind of the biggest roadblock, because it means that's an additional privacy leakage, right? Like by looking at the noise, we have even more privacy leakage than before. This actually establishes quite an important negative result, which is that approximate homomorphic encryption is not actually composable with differential privacy, by which I mean that if you use approximate homomorphic encryption, you need to choose your differential privacy parameters to reflect that. That's new in this work. And the third is that homomorphic encryption noise exposure can compromise security. So if you've got a really strong adversary who's who can see your encrypted ciphertext and see your presentation at the end, you've given the game away. That's really going to compromise the security of your scheme. Cool. Yeah. So I'm going to conclude. And I haven't applied what we talked about today's slide. The first thing I would think about, I don't know what you do, I don't know what your job is, but if you're in an organization that uses data, I think about like what is the data pipeline for your organization. I know this is pretty non-trivial, right? Like where did we get this data from? What departments see it? Like who are we sharing the results with? This is already a pretty big to-do. Cool. If you think about these exposures and you're not quite comfortable with them, or your regulator isn't quite happy with them, can you integrate privacy-enhancing technologies? In particular, the two we've talked about today, homomorphic encryption and differential privacy. And third, and I think this is the real moral of this presentation, I hope, is that does your use of these technologies make sense in the context of the entire pipeline? So are you paying a 10,000x overhead to encrypt some data that you procured from public sources? Are you paying a 10,000x overhead and then you're just exposing the results publicly, which means that people can reverse engineer your data set? Are they, you can't really segment these stages off, right? Cool. All right, thank you so much for your attention. Feel free to catch me offline or any questions now. Thanks. It's looking good. Oh, hello.
Hello. I have two questions, I think.
Oh, okay.
The first one is, could you give an estimation of what you gain by the free differential privacy that you propose? Like, is differential privacy costly to make? And so it's nice to...
Yeah, it's pretty costly. Yes. So we achieved privacy budgets of about 2. Yes. If we didn't consider the message dependence, this would be a massive, massive win. We'd be getting privacy budgets of about like 0.01. Like it would be really, really good. And that's kind of noise you'd be adding anyway to get that privacy budget. So yeah, but it's once you consider this message dependence, it becomes a much, much more costly thing to add. Does that answer your question?
Yeah.
Yeah.
And sorry. The second one is, was there a problem between, if you had, how do you differentiate properly or maybe it's at the point, the noise for encryption, for the homomorphic encryption, does it translate, or can it translate into false decryptions or false interpretation of data for the differential privacy part? Like, can there be confusion because of the use of that noise?
Do you mean can it corrupt the result?
Yeah, somehow, yeah.
Yeah, yeah, it can. We were trying to sort of match exactly the homomorphic encryption noise to like the least that would be needed for differential privacy. So we were kind of arguing it's noise that has to be there anyway. But yeah, it can definitely be the case that like differential privacy is definitely a trade-off between privacy and accuracy, and you can completely corrupt your result if you have certain functions can be very sensitive to changes in the database. So you have to add large amounts of noise to mask that difference, and that kind of destroys the quality of your result. Yeah, completely.
Okay. Thank you.
Hi, I'm very new to the homomorphic encryption. But I'm curious, it sounded like from your presentation that there is a need to protect the homomorphic encryption noise. And so if I'm using homomorphic encryption to protect the data, I'm also having to protect the data and now also protect the noise. How is that?
Okay, this is a really good question. So in typical schemes, like the one Marc talked about and others, the noise is removed during decryption. So as long as your decryption is happening in kind of a secure environment within your organization, you're sort of fine. Like the noise is gone and you don't need to worry. The question of the security model in which you have to worry about this kind of noise exposure is quite a strong one. It essentially means the server has to see the results of decryption. It's going to be very use case to use case, whether that is, there's techniques to mitigate this, there's kind of noise flooding techniques. These would also give you differential privacy. But yeah, in a general setting, for most schemes, this is not a problem, but yes, good for picking up on that, yeah.
The pipeline, I think it's very correlated to most of the companies.
Oh, cool.
Most of the data analytics we dealt with is internal to the company.
Right.
We don't expose this outside, right?
Okay.
So
you
differential privacy.
Don't use like AWS? You don't use Google Cloud?
Okay. So what we do is like a Snowflake or something that is part of the end of the pipeline, right?
Okay.
So one angle to it is tokenization, where the data is sitting, the data type is not changed. Whereas as part of the encryption, the data type is changed, the value of the data is changed.
Yeah.
So there is a cost tied to the encryption versus tokenization, right? In the differential privacy, if there are multiple business units within an organization,
right,
where we give only subset of the teams access to the analytical data store. So I feel that tokenization plays a better perspective compared to the encryption. Is that a true statement?
Yeah, I suppose if you're happy with that level of exposure, I mean, I could also say that homomorphic encryption does potentially enable like massively reducing like your attack vector, right? Because you could then store that data in like a hugely encrypted form. Maybe not, but yeah, I think in general, if everything's staying internal and you're happy with everyone who's seeing it, but you're talking about a lot of people interacting with that data in its raw form, right?
Correct.
If it's very, very sensitive data, that might be a big price to pay, right?
Got it.
Yeah.
Yeah, it's based on the use case to use case.
Exactly. Yeah. It's going to depend on the structure and size of the organization, as well as the data that's being handled, right? And the regulatory environment. Yeah.
Got it.
Yeah.
Thank you.
Cool. Thank you.
Just one more question.
Of course.
In regards to that noise, is that, then you say it's thrown away as part of the encryption process?
Yeah, decryption, yes.
Decryption process. So the noise, is that ephemeral type data?
Yes.
And what type of noise is that when you sharing noise?
As in, what distribution does it come from?
I'm not well, I don't know when you use the term noise.
Right.
What does that really mean?
So it comes from the cryptographic assumption that we rely on for these schemes. So we rely on something called learning with errors. And that means there's kind of this error term. In Marc's law, it was like an E. And this is what we call noise.
Okay.
Does that answer your question? Yeah, thank you. Yeah. Thank you.